In this session and the next one, we will be solving assignment number 5 and assignment number 6. You have seen me solving assignment number 1 through 4 so far, and what we are going to do in these two sessions, that the problem solving will be done by the teaching assistants who have been involved in this course right from the beginning. They are regular PhD students at IIT Kanpur Physics Department, and they have been responsible for correcting the assignments, generating their solutions, and so today they will be sharing these solutions that they have done with you. Assignment number 5 will be solved by Mr. Rabit Singh and Ms. Paramita Dasgupta. So, here is Rabit Singh.
In the first question, you have to calculate this integral cos theta prime sin theta prime d theta prime d phi prime over r square plus small r square minus 2 r capital R cos theta prime cos theta plus sin theta prime sin theta cos phi minus phi prime. So, what we will use this symmetry, phi symmetric density of a spherical cell to calculate this integral. So, first what we will do, we will calculate the potential due to a phi symmetric density for a spherical cell. We know if we have given a density sigma theta equal to cos theta. So, for this density we have seen in the lectures that potential. So, we have a spherical cell at which this density sigma is included, and we have seen in the lectures that the potential due to this spherical cell at point vector r is given by this expression, which is r over 3 epsilon naught cos theta for r is smaller than capital R, and for r is greater than capital R, this potential is given by r cube over 3 epsilon naught cos theta over r square. R is greater than capital R. So, we will use this answer to calculate this integral. So, again V r equal to 1 over 4 pi epsilon naught sigma naught theta over vector r minus vector capital R d theta d phi. So, if sigma theta is equal to cos theta, we can write this answer as, so let me try this way. Okay. So, if the given density sigma theta prime is cos theta prime, so we can write this cos theta prime, and for the spherical system this surface element is given by r square sin theta prime d theta prime d phi prime. So if the given density is cos theta prime, we can write this as r square sin theta prime d theta prime d phi prime over vector r minus vector r prime, where vector r prime vector r prime refers to the point on the spherical shell. So we can write this r square over 4 pi epsilon naught cos theta prime sin theta prime d theta prime d phi prime upon vector r minus vector r prime. So if we compare the two answers, so we can see this potential is equal to, because we know the answer for this potential, so we can compare this with those answers which is given by r over 3 epsilon naught cos theta for r is smaller than capital R, and equal to r cube over 3 epsilon naught cos theta over r square for r is greater than equal to capital R. So we can see that we can write this as cos theta prime sin theta prime d theta prime d phi prime over vector r minus vector r prime 1 over 4 pi epsilon naught r square equal to r over 3 epsilon naught cos theta for r is smaller than equal to capital R, and equal to r cube over 3 epsilon naught cos theta over r square for r is greater than equal to capital R. So we can write this as sin theta prime cos theta prime d theta prime d phi prime over vector r minus vector r prime equal to, so we can see this can be written r over capital R square into 4 pi cos theta for r is smaller than capital R, and equal to 4 pi r over 3 cos theta over r square for r is greater than equal to capital R. So here in spherical coordinate, vector r minus vector capital R can be written equal to mod of vector r minus vector capital R can be written equal to r square plus capital R square minus 2 capital R small r cos theta prime cos theta plus sin theta prime sin theta cos phi minus phi prime. So, if we write the value of mod r minus vector r, then we can see the integral sin theta prime cos theta prime d theta prime d phi prime over r square plus capital R square minus 2r capital R cos theta prime cos theta plus sin theta prime sin theta cos phi minus phi prime. So, which is nothing but the integral we have to calculate. So, this is the answer for the first questions. So, our next question is question number 2. Question number 2, we have a uniformly charged spherical cell So, this is rotating around the z axis. So, if we take a surface element on this spherical cell, we can see that every element is moving around the z axis with the angular velocity omega. So, the velocity of the surface element ds is given by, so this angle is, so if vector r makes the angle theta with the z axis, we can see that this is the radius of the circle at which this surface element ds is moving. So we can see this is the circle at which ds is moving. So, the radius of this circle is given by r sin theta. So, you can see Vr is given by r sin theta into omega, which is nothing but the radius into the angular velocity. So, current density, which is Jr, is given by sigma, means whatever density is there, sigma into Vr, but this is the surface density. So, if we write the volume charge density, volume current density, we will write this as delta r minus vector r into Vr. So, we can see this surface element moving along the phi direction. So, the direction of Jr would be along the phi cap direction. Okay. So, this is the answer for the second question.
Another way of looking at the answer for the same problem would be, if I take this spherical shell and consider a band here. This band has an area which is 2 pi r sin theta times r d theta. This is the total area of this band. So, that this is 2 pi r square sin theta d theta. The charge on this band, net charge q, is 2 pi r square sin theta d theta times sigma. And this charge is going around, it goes around in per second, it goes, the charge goes around in per second omega over 2 pi times. So, the current that this band is giving is nothing but 2 pi r square sin theta d theta times sigma times omega over 2 pi. Let us do some cancellations. This 2 pi cancels and you get r square sin theta d theta sigma omega. That is the current going at the surface. So, the surface current density will be this current divided by the length out here, which I am showing on the red on this sphere, which is r d theta. So, this will be r square sin theta d theta sigma omega divided by r d theta. Let us again do some cancellations, d theta cancels, r cancels, and you get r sigma omega sin theta. So, the surface current density K is sigma r omega sin theta in phi direction, and when I express this as a volume current density, J would be equal to K times it is at r minus r. So, this becomes sigma r omega sin theta delta r minus r phi, which is indeed the same answer as earlier. So, what we have tried to do is give you two different ways of looking at the same problem.
So, now we are going to solve problem number 3. So, in problem number 3 we have to calculate the integral d phi prime dz prime over vector r square plus small r square minus 2 small r capital R cos theta cos phi minus phi prime plus z minus z prime, the square of z minus z prime. So, we have to calculate this integral. So, what we will do again. So, we have a cylinder having a uniform density sigma. So, first I will make a Gaussian surface which is cylindrical, because here is the phi symmetry. So, we can see electric field is perpendicular at every point on this surface, which is along the r cap direction. So, and surface element is also in the same direction, which is r cap. So, according to the Gauss's law, we can write, and length of this surface is capital L, the radius of cylindrical cell is capital R, and the radius of Gaussian surface is small r. So, we can see we will use the Gauss's law, which is E dot ds equal to, so charge enclosed, Gauss's law equal to charge enclosed in the Gaussian surface upon epsilon naught. So, we can see charge enclosed would be equal to the surface area of the cylindrical cell, which is given by 2 pi capital R into L into charge density upon epsilon naught. So, because E is constant at every point, we can write this as ds equal to 2 pi capital R into capital L into sigma over epsilon naught. So, ds is the surface area of the Gaussian surface, so which is 2 pi small r into L equal to 2 pi capital R into L sigma over epsilon naught. So, the electric field E is equal to, because L 2 pi would be cancelled out. So, electric field is given by R sigma over epsilon naught into R. So, now because we know the electric field at point R is sigma capital R over epsilon naught into R. So, the potential Br is given by R to capital R E dot dr, where R is the reference point. So, what I will do, I will take the reference point at the surface of the cylindrical shell. So, this would be equal to E sigma capital R over epsilon naught into R dr, which is equal to sigma R over epsilon naught ln R prime R to capital R. So, this is given by capital R over epsilon naught ln capital R over small r. So, this is the potential. So, this is the potential due to the cylindrical cell, cylindrical cylinder having the uniform density sigma. So, I will use this result to calculate for R is capital than capital R, and inside the cylinder E equal to 0. So, inside the cylinder potential is constant, and which is would be equal to whatever potential would be on the surface of the cylindrical cell. So, if we take potential at the reference point 0, that is Vr equal to 0. So, we have Vr equal to 0 inside the cylinder, and outside the cylinder Vr equal to this one. So, again if I write, if you have given a cylindrical cell having a uniform charge density sigma, so potential at point P and this is the charge element which is given by R d phi prime dz prime into sigma. So, this is the charge element. Due to that, you have to calculate the potential at point P. So, this is vector R. So, we can see the potential dB. So, the potential at point P will be the sum of the potentials due to the all the surface elements, which is given by the integral Vr equal to sigma R d phi prime dz prime over vector R minus capital R, which is the distance from the charge element to the point at which you have to calculate the potentials. So, we know the answer of this problem which we have calculated. So, this VR is given by, this is sigma r over epsilon naught ln vector ln r over small r for r is greater than capital R and equal to 0 for r is smaller than capital R. So, if we see this integral, you can sigma r would be cancelled out, and there is a one more factor, that is 1 over 4 pi epsilon naught. So, epsilon naught would be cancelled out. So, we can write d phi prime dz prime vector r minus vector capital R. We say this is r prime because equal to 4 pi ln vector r over small r for r is greater than equal to capital R and equal to 0 for r is smaller than capital R. So, if we see this integral, we can write vector mod of vector r minus capital R, which is r square plus capital R square minus 2r capital R cos pi minus phi prime plus z minus z prime whole square. So, if I put the value of vector r minus capital R, mod of vector r minus vector capital R, so that is d phi prime dz prime over r square plus capital R square minus 2r capital R cos phi prime phi minus phi prime plus z minus z prime whole square. So, this is nothing but the integral which we have to calculate. So, this is the answer for problem number 3. So, in the assignment there is a factor which is 2 pi was not there. So, that is the just typing error. In question number 4, we have a disk which has the uniform magnetization along the z direction. So, magnetization is along the z direction, which is this. So, if I calculate the bound current, which is sigma B, which is given by m cross n cap, so here if I write vector m which is along the z direction, and we can see the surface element is also along the z direction. So, sigma b equal to 0. So, this is a kb. Vector kb. So, and the volume charge density, which is jb, is given by del cross m, because we have a uniform magnetization. So, this is also 0. So, outside the disk m equal to 0, because magnetization is only on the disk, and because there is no free current and no bound current. So, we can write B is also equal to 0. So, this is the answer for problem number 4.
A couple of comments on the solution and a different way of looking at it. What you were told is that K B, which is m cross n, is 0, which in effect it is on the upper and the lower surface, but you may raise a question, and the question would be, if I have this disk and m is in the z direction, on the side surface there is an n, so that when you take m cross n, you do see a current on the periphery of the disk. So, if I look at it from the top, this current may be going like this. However, what we have done in this problem is that this is a thin large disk in which the extent or the radius of the disk is much larger than the thickness. And therefore, if you think maybe the surface current gives rise to some magnetic field, yes it does, but it is very small, effectively 0, because large R would give a very small field at the center. And therefore, what was done was correct, but if you have a question that there may be a peripheral current, you are right, but that current contributes nothing to the magnetic field. You can also look at the same problem from the point of view of H, or the auxiliary field that we were talking about. Now, there is an M like this. You recall that we had done in the lecture that divergence of B is 0, and therefore, divergence of H is equal to minus divergence of M. What that gives you? You see, if you look at it across, M is finite and suddenly goes down. So, M is like a delta function, or it gives rise to a surface magnetic charge, if you like, surface magnetic charge. You can see out here divergence of M is going to be minus M, and on the other side divergence of M is going to be plus M, because as you go across, M is increasing and then M decreases. And therefore, when I take minus of divergence of M, it is as if on this disk, for calculation of H, there is this positive magnetic charge here, negative magnetic charge here, and the kind of field it will give rise to would be like the electric field. So, H will be in the other direction here. So, H inside will be equal to minus M, and H outside will be equal to 0. I also know that B is equal to mu 0 H plus M, and therefore, B inside will be mu 0 minus M plus M, which is 0, and B outside, since H is 0, will be 0 and M is 0 there. So, this is the same as the previous, as the problem was done earlier. Both give you the same answer. We have given you two ways of looking at the same problem, either through the bound currents or by an electrical analogy. This also answers the question to question number 5.